It is my pleasure to present to you the Professor Seok-Jin Kang, who is the closing plenary speaker for 2009 PRIMA Congress. Professor Kang received a PhD degree from Yale University in 1990, and then he he had a position at the North Carolina State University from 90 to 92. After that, he was the visiting mathematician at MSRI. From 93 to 94, he held a position at the University of Notre Dame. And then he returned to Seoul National University in Korea in 1999. After a couple of years there, he moved to Korea Institute for Advanced Study, where he stayed 3 years there with me. And then he again returned to Seoul National University. So he had some lot of the positions from the different institute, all of which are very prominent ones. And just the months ago, Professor Kang was awarded the prize for most outstanding scientist and engineers in Korea. After this talk, probably some colleagues will celebrate for his award. Today, Professor Kang will talk on the subject perfect crystals for quantum affine algebra and combinatorics over Young worlds.
Okay, thank you very much for the invitation. And thank you very much for remaining with me until the last moment. And I feel quite honored to be the final speaker of the Congress. And on the other hand, I feel quite awkward and sad because I have been thinking that the final speaker is supposed to be one of the senior persons. And I hope this doesn't necessarily mean that I already became a senior mathematician. I'm still young because, as title said, I will talk about combinatorics for young worlds. Well, let me start with a very simple-minded observation, which is quite familiar to algebraic geometers and deformation theorists, and which was noticed by Kashiwara and Lustig. So let Q be an indeterminate, and consider a vector space of the rational function field in Q, and let A be the subring of Laurent polynomials, and A naught denote the ring of regular functions at 0, and A sub infinity denotes the ring of regular functions at infinity. Then we'll consider the A lattice of V super A of V, and A naught lattice and A infinity lattice of V. So we'll denote by L and L infinity the A naught lattice and A infinity lattice of V respectively. And consider the intersection of these three lattices. Then the triple V super A L L infinity is called the balanced triple. If E is a lattice, is actually Q lattices in V super A L and L infinity. Okay. Then from this notion, well, we can recover V by extending the scalar of E. then the notion of balanced triple can be characterized as follows. So, well, the following statements are equivalent. If the triple is balanced, then there is natural projection map from E to the L of Q mod L, and that should be an isomorphism. Also, the natural projection map from E to the L infinity over Q inverse L infinity is also an isomorphism. So, one can consider the inverse of this natural isomorphism, which is denoted by G. Then, to understand the vector space V, we can concentrate and focus on the vector space L mod QL. And if we understand the basis of L mod QL, which is called the crystal basis or local basis at Q is 0, then one can recover many information of vector space V. So the corresponding vector basis of local basis Q is 0 will be called the global basis or canonical basis. And our idea is the following. So we try to understand V, but here the E is the intersection of all lattices. Then there is an isomorphism between E and L mod QL. So the projection map is an isomorphism, and the converse is denoted by G. Then we try to understand this, maybe I'm too late, that this basis at Q is 0. First, we understand this base at Q is 0, then recover the so-called global basis or canonical basis for the whole vector space V. That's the idea. So now, to apply this idea to the quantum groups, let us recall the definition of quantum groups very briefly. So let A be a symmetrizable generalized Cartan matrix, and P check is the free abelian group, which is called the dual weight lattice, which is generated by HIs and D sub S. And pi check is a set of simple coroots, and P is the weight lattice, and pi is a set of simple roots. So this quintuple is called the Cartan datum. And to each Cartan datum, we can associate an infinite dimensional, usually infinite dimensional Lie algebra, which is called Kac-Moody algebra, which is the Lie algebra generated by the symbols E sub I, F sub I, and H with the following defined relations. So H is commute, E sub I, Fj is almost commute, and H, where adjoint action of H acts diagonally, and this is this so-called set relation. So you apply EIs enough times on EJ, then you will get 0. And this is a generalization of a presentation given by Serre for finite dimensional simple Lie algebras. And well, around 1968, Katz and Moody independently discovered this class of Lie algebras, which are usually infinite dimensional. And so, for example, so finite dimensional simple Lie algebras are Kac-Moody algebras, and affine Kac-Moody algebras are examples of Kac-Moody algebras. And these two classes are of main interest to the people. And for beyond affine algebras, actually very little is known now. So we will focus on category of good modules. So we denote by O sub integrable the category of modules of Kac-Moody algebras, which has weight space decompositions. Here, M sub lambda is the common eigenspace for the operator H. And there are finite many upper bounds for the weight. And the elements E sub I and F sub I act locally nilpotently on each M. Then what is known about this category is that, well, when the dimension of weight spaces are all finite, we define the character of a module to be the formal power series whose coefficients are given by the dimension of weight spaces. Then, what is known for this category? Well, for dominant integral weights, there is a uniquely determined irreducible module, which is called irreducible highest weight module. Then, this highest weight module lies in this category whenever lambda is a dominant integral weight, and every simple object in this category is isomorphic to some highest weight module V of lambda, and this category is semi-simple. So every module in this category is completely reducible. Now, for quantum groups, well, we deformed the notion of Kac-Moody algebras to the notion of quantum groups. So actually, we deformed the universal enveloping algebra of Kac-Moody algebra to quantum group. So that quantum group may have to be referred to as quantized universal enveloping algebras. So it is an associative algebra with generators E sub I, F sub I, and Q to the H with the following defined relations. So these defined relations can be understood as certain Q twist version or Q deformed version of defined relations of the Kac-Moody algebras. And here we can also define the quantum version of set relations. Now, here, these are the notations, and these are Q integer and Q factorials and Q binomial coefficient. And we define the category of good modules in a very similar way to those for Kac-Moody algebras. So the modules must have wave space decomposition. Here, wave spaces are the common eigenspaces for Q to the H, and eigenvalues are given by Q to the lambda of H. And then these two are same. So there are finite many upper bounds, and EI and FI should act locally and nilpotently on the modules in this category. And the character of the modules for MQ is also given by the formal power series, whose coefficients are given by the dimension of wave spaces. Now, well, we also can have similar theorem for this category. So the irreducible highest weight module belongs to this category if and only if lambda is dominant integral weight. And every simple object must be isomorphic to irreducible highest weight module, and this category is semi-simple. But it was known by Drinfeld and Jimbo and Lustig and others. The quantum group UQ of G is a deformation of the universal enveloping algebra of Kac-Moody algebra. So as Q approaches 1, the structure of quantum group approaches to that of U of G. And the representation theory of quantum group in this good category are almost the same as the representation theory of Kac-Moody algebras in category O integrable. So pictorially, one can see this way. So where you have Kac-Moody algebras and its universal enveloping algebra, and consider its integral representations category O integrable. And if we deform the two each indeterminate Q, we have a family of, we have Hopf algebra, which is denoted by UQ of G, and corresponding module, and their wave spaces are the same. I mean, dimension of wave spaces are the same. And we actually would like to compute the character of a module because the character is the first clue to understand the structure of the module, and at least it gives us how to measure the size of the module in an elementary way. And second, character is an algebraic invariant. So the isomorphic modules have the same character. So if you have different characters, then you can say that these two modules are different. And also, in many cases, the character stands for important and interesting mathematical quantities. For example, it appears as symmetric functions in combinatorics, and also modular forms in number theory, and also it can express one-point functions. I mean, the quotient of string functions over character can be understood as one-point functions in solvable lattice models. For this reason, one of my friends in Melbourne, who is Arun Ram, once mentioned or claimed that the computing character is the heart of combinatorial representation theory. Whether heart is more important and brain is more important, that depends on people, but the heart is quite important. So what Lustig theorem tells us is that the character is the same for all generic Q. So natural question is, when is the situation simple? So for what value of Q the situation simple? And since my experience from elementary school days, for these problems, the answer should be 0, 1, or a negative 1. Right? So our answer should be, but by the way, when I gave this talk in Korea many years ago, one of the audiences in here asked me, actually suggested, when I asked when is the situation simple, and his answer was 6. I don't know where 6 came from, but that person is right here. I will not tell you who he is, but. So my answer is Q is 0. So what does it mean? Well, given the representation in this category, fix an index at I, then using the SL2 decomposition, one can express every weight vector as the sum of these expressions. So here, each UK should be annihilated by E sub I, and here Fi to the K denotes the divided power of Fi to the K. And it is called an I-string decomposition of this element U. And we define modified root vector operators, which are called the Kashiwara operators, EI tilde, Fi tilde, as follows. So we just lower the exponents by 1 and raise the exponent by 1. Actually, but in terms of root string, this is, you raise root string by alpha, and you actually lower the root string by alpha. And with the aid of these operators, one can define the notion of crystal basis in an elementary way. So a crystal basis of a module is a pair L and B, where L is a free A non-module of M, so that we can recover the whole module by extending the scalar. And B is the basis of L mod QL. And these are rather natural and technical conditions. And finally, for B and B prime, Fi tilde and Ei tilde should be almost inverse to each other. And well, I have told this many times, but when I was in junior high school days, I read 2 novels in English, only 2. Oh, 3 maybe. One was Love Story, the other was Animal Farm. And in Animal Farm, where there was some sentence like that, all animals are equal, but some animals are more equal than others. So to define a notion of crystal basis, all the properties should be equal, but some properties are more equal than others. And I think that's 2. That means B is a basis at Q is 0. And 7, that means the operators Ei tilde and Fi tilde are inverse to each other. So one can define a graph structure on this set B by assigning I colored arrow from B to B prime whenever Fi tilde B is B prime. And moreover, point is that the most of combinatorial features of the representation are reflected on this crystal graph. For example, if you want to compute the dimensional weight spaces, then we have only to count the number of elements in the set P sub lambda. So the natural question would be whether there exists crystal basis for good modules. And we have seen that the modules in category O integrable are completely reducible, and irreducible objects are irreducible high-state modules. So consider irreducible high-state module, and consider the A form, integral form of the quantum group, which are generated by divided powers and this appropriate modification of the elements in U naught. And A form of high-state module for lambda is defined by this submodule generated by this high state vector. Then let L of lambda be the free A naught submodule spanned by all the vectors of this form. So you apply Kashiwara operators Fi tildes on high state vectors as much as possible and just collect them. And well, let Q be 0 and collect the non-zero vectors among these vectors. Then Kashiwara's theorem says, maybe more, I need more preparation. Here, consider the so-called bar involution, which is Q algebra automorphism defined by this. So Q goes to Q to the infinity, EI, Fi are stable, and Q to the H goes to Q to the negative H. Then it induces an involution on the high state modules. And let us denote by L lambda bar the bars of elements in L of lambda. Then what Kashiwara proved was, and also known by, well, Lustig also proved the similar thing using different approach. So the set triple V super lambda, V super A lambda, and L of lambda, and L of lambda bar is a balanced triple of the irreducible high state module, and L of lambda and B of lambda is a crystal basis. Actually, the uniqueness can be also proved. Therefore, let us recall our original motivation. So, to understand irreducible high state module V lambda, we consider the balanced triple. Then when Q goes to 0, we are interested in finding the basis of L lambda over Qn lambda. Then we can recover the basis, global basis G of lambda. That is our picture. So, natural question is how to realize the crystal basis B of lambda and how to construct the corresponding global basis G of lambda out of crystal basis. So these two are main problems in crystal basis theory, and I will talk about this maybe for the remaining time. And so, let me give you an example of the realization problem of a crystal graph. So, for example, for SLN, the crystal graphs can be realized as a set of semi-tanh tableau of shape lambda. And also, the crystal graph for irreducible high weight modules can be realized as a set of irreducible components of certain Lagrangian subvarieties of Nakajima cube varieties. And when lambda is infinity, I mean for UQ minus G, then actually it is this Lagrangian subvarieties of Lustig's varieties. And Lustig realized crystal graphs where canonical basis or global basis using simple Purvis sheaves. And I will skip for generalized Kac-Moody algebras. Now, let us focus on the affine Kac-Moody algebras. And I'm trying to check the time, but yes. So I'm supposed to speak for 45 minutes, right? Right. So let us focus on affine Kac-Moody algebras. So for affine Cartan datum, let UQG denote the quantum affine algebra. I just realized that I'm trying to speak too fast. So there is Korean saying that you should take time whenever you are in a hurry. So let me take time. Speak slowly too. For an affine Cartan datum, let UQG denote the quantum affine algebra. And let us consider the corresponding weight lattice. And it is called the classical weight lattice because we forget the effect of imaginary root here, but we will get back to the effect of imaginary root soon. So here, let P bar be the classical weight lattice, which are generated by fundamental weights, and P L bar plus be the set of dominant integral weights of level L. And here, C denotes the canonical central elements. Then the subalgebra generated by E sub I, F sub I, and K sub I plus minus 1 is also called the quantum affine algebra, and which is kind of derived subalgebra of the quantum affine algebra. Then, consider UQ prime G crystal basis B. UQ prime G can have finite dimensional modules, and it can have finite crystal. And for the element in B in this crystal, let us denote by epsilon of B the sum of dominant integral weights whose coefficients are given by epsilon IB. Here, epsilon IB means the number of I arrows coming into B. And similarly, we define phi B. Here, phi sub IB denotes the number of I arrows coming out of B in the crystal graph B. Then, a finite crystal B is called perfect if P tensor B is connected and there is uniquely determined weights which satisfies this condition. And third, but again, the more equal properties than others is the last one. So for each dominant integral weight of level L, there are uniquely determined elements B super lambda and B sub lambda, whose epsilon is lambda and whose phi is lambda. So from this definition. Okay. So such a crystal is called perfect. For example, for A to 1, this crystal is perfect because, for lambda naught, for example, this is the vector whose epsilon is lambda naught. This is a vector whose phi is lambda naught. But again, this is perfect for B31. So for lambda naught, this element is the one whose epsilon is lambda naught, and 1 bar is the element whose phi is lambda naught, etc. But this crystal is not perfect because for lambda 1, there are two candidates whose epsilon can be lambda 1, and these two elements have phi lambda 1. So this graph is not a perfect crystal. So what is so perfect about perfect crystal? Then for perfect crystal, we can have following isomorphism theorem. So here, if we have irreducible high-state crystal for irreducible high-state module, then in this perfect crystal, we have P sub lambda, whose phi is lambda. Then consider its epsilon. Then this irreducible high-state crystal is isomorphic to the tensor product of these two crystals. On the other hand, well, this is an infinite crystal, this is a finite crystal. You take the tensor product, then it is still connected and it should be isomorphic to B of lambda, something like that. That's the main idea. And here, this means the authors, Kashiwara, Biwa, Mizura, Nakashima, Nakayashiki, and plus one more K. And so this fundamental isomorphism theorem enables us to do so-called path realization of irreducible high-state crystal B of lambda. So you just repeat this isomorphism theorem, then you will get a sequence of B0, B1, etc., which is determined by this idea. Then this infinite sequence, which should be understood as a semi-infinite tensor product, is called the ground state path of weight lambda. And a sequence is called the lambda path in B if its tail is the same as the ground state path. And consider the set of all lambda paths and give a crystal structure on the set of lambda paths. Then the main theorem is that the lambda path is from an irreducible high-state crystal, and which is from a crystal which is isomorphic to irreducible high-state crystal. And one can calculate character of the free lambda by enumerating the weights of each path in this crystal. Now, this is an example of so-called path realization, and this is another example. And so this theory of perfect crystals have an interesting applications to physics. For example, the theory of vertex models can be explained in the language of representation theory of quantum affine algebras. In particular, the one-point function, which is the probability for certain configuration, can be expressed as quotient of string function over this character. But I would like to understand this irreducible high-state crystal in terms of more combinatorial object. And let us go back to the work by Mizra and Miwa. So here, let G be the affine Kac-Moody algebra of type AN-1, and lambda be the fundamental weight lambda naught. And a colored Young diagram is a Young diagram of this form, which are colored this way. So you have seen the zeros are in diagonals, 1, 2 are in diagonal. Well, why do I call this Young diagram? Well, I know there are many different conventions. This is the, I think, maybe usual convention for Americans. I think French people use this way, and I heard Russians use this way. So this is my own way, and I have my own reason. But which can be explained soon. So, and this Young diagram is called n-reduced when the difference of the columns are always less than n, then it is called n-reduced. Then let us denote by z lambda naught the set of all colored Young diagrams, and y lambda naught the set of all n-reduced Young diagrams, and f lambda naught the space spanned by all colored Young diagrams. Then what Mizra and Miwa proved in 1990 was that this has crystal structure, and the set of reduced Young diagrams is isomorphic to the irreducible high-state crystal P lambda naught, and this space, which can be called Fock space, is a representation of the quantum affine algebra of type AN-1. And well, this is an example of the N3 reduced crystals. But what's known is that let Hn zeta denotes the Hecke algebra of type A with at root of unity. Then it is known by different James, Graham Letter, and many others, and Hupf-Schmidt. Simple modules can be labeled by n-reduced Young diagrams. And moreover, Lascaux, Leclerc, and Thibon found an algorithm of computing the canonical basis or global basis corresponding to the n-reduced Young diagram. So let Y be an n-reduced Young diagram. Then there should be corresponding canonical basis element. And they found an algorithm of computing this. So when Q is 0, it is the same as Y. And conjecture that if you plug Q is 1 here, then this coefficient matrix gives the decomposition number of simple modules corresponding to n-reduced Young diagram inside Specht modules corresponding to any colored Young diagram. And it was proved by Ariki. And actually, Ariki proved more. So here one can express this theory in terms of this table. So left-hand side is quantum affine algebra AN-1,1. Right-hand side is Hecke algebra, finite Hecke algebra at root of unity. And for a Young diagram, there is naturally determined indecomposable module, which is called Specht module. And for an n-reduced Young diagram, Specht module has simple quotient, which is denoted by d super y. Then the set of n reduced Young diagrams forms a crystal which is isomorphic to irreducible high-state crystal, B lambda naught. And in right-hand side, consider the grothendieck group of each h and zeta, and take the direct sum of up to infinity. And by using induction and restriction functor, one can determine graph structure here. And it turns out to be true that they are actually isomorphic to irreducible high-state crystal. And here we have Fock space and LLT algorithm. And then we will get coefficient matrix functions k, y, z. And if we plug q is 1, then we will get decomposition number. This is the story. So natural question is, well, actually Ariki proved more. So this is for level 1. And for negative part of quantum group, then we should consider affine Hecke algebras. And if we consider cyclotomic quotient, which is called Ariki-Koike algebra or cyclotomic Hecke algebra, then the grothendieck group gives irreducible high-state module for higher level. So this is the whole picture. So starting from affine Hecke algebra, you go down to the cyclotomic quotient, and at level 1 quotient, this is the finite Hecke algebra, and we will get level 1 high-state modules. This is the picture for AN minus 1 case. So natural question is how to generalize this picture to other quantum affine algebras. And at least for level 1, and my idea is once you are done with the level 1, then you can extend to level L by taking tensor product. So for level 1, for so-called classical quantum affine algebra, the left-hand side of the table is complete. And the idea is Lego blocks and Tetris. So I think everybody knows Lego block. And some people do not seem to know what Tetris is. So what is Tetris? Tetris is, tetra is 4, right? So you have 4 squares, and it makes some forms. Then it will fall down from the sky. Then you need to find the right place, and then fit into the right place. Then you are trying to erase a horizontal bar. Then you will win. Well, you will eventually lose, but the thing is that how long you survive. But it's like life, you eventually lose. But is that funny? All right, so that's the idea. So how do we play? So here are the blocks. So color, well, we will give an example of B and 1. 0 and 1, this is half thickness blocks. And 2 to the n minus 1, these are regular boxes. And for color n, this is half height blocks. And I will use this notation. So if you put star upper left corner, then that means we place block in front. And if we place star in lower right corner, then that means we place the block at the back. So we first start with the blocks at the back, 1, 0, 1, 0 blocks at the back, and we put 0, 1, 0, 1 blocks in front, and you pile up blocks like this. And I assumed gravity applies to the down and right hand side. So if you look at the diagram from the front, then you will get this, which is Young diagram. But what we are doing is actually we have a wall of thickness 1. So I call it Young wall. So here Young is named after Alfred Young. It doesn't have anything to do with the young and old. So this is called Young wall. So again, ground state wall is this, 1, 0, 1, 0 at the back, and going to the left, infinity. And by gravity, this is not allowed. Okay? It will fall down. And this is not allowed either. Okay? So a young wall, well, you have the notion. I mean, the wall, by applying gravity, after applying gravity, I mean, you obtain a young wall. And the full column in a young wall means its height is integral and top is full block. I mean, top with unique thickness. So if height is half height, then it's not a full column. And if thickness is half thickness, then it's not a full column. And a delta column is one cycle pattern. So here, so one cycle pattern is here 0, 2, etc., n-1, n-1, 2, 1, 1. So this part is one cycle. And why it's called delta? Because those who are familiar with Kac-Moody theory will realize that this is the imaginary root for Bn1 type. Okay? And well, a young wall is called proper if there are no full columns of equal height. So, well, if two columns are not full, then they are allowed to have equal height. But full columns are not allowed to have equal height. And a column is removable delta column if it can be removed to have proper young wall. And a young wall, proper young wall is called reduced if there is no removable delta column. So what I have described here was a generalization with colored Young diagrams and n-reduced Young diagrams. So colored Young diagrams are generalized to perfect Young, proper Young walls, and n-reduced Young diagrams are generalized to reduced Young walls. And for example, this is not a Young wall at all. And this is proper but not reduced because here one can delete this part. And does the bell mean that I have only 5 minutes left or 2 minutes left? Okay, right-hand side is proper and reduced. And we can determine crystal structure here. So here, if a block can be removed, we say it's removable. I mean, removed to keep a Young wall, proper Young wall. And a slot is called admissible if you can add a place here. So for removable blocks, we place minus sign and double minus signs. And for admissible slots, we put plus and double plus signs. And if it is both removable and admissible, then we place negative and plus sign. And cancel plus minus pair, then we will obtain the sequence of negatives followed by positives. So what we should do is, so here is a Young wall, and here is one block is falling from the sky. He then identify its color. If it's I, then just compute these sequences and find this so-called reduced signature. Then place its leftmost plus. Place the block. So that's why it's called Tetris. I mean, from the block, you identify the block, color of the block, and calculate this in a Bezier way and place it. Then that's Fi tilde. Then this gives, I will not give you an example. I mean, at least here you place n block here and you remove this block here. That's En. But then the claim is that for these classical affine algebras, let us denote by Z of lambda the set of Young walls and Y of lambda the reduced Young walls. Then the Z of lambda is a UQG crystal, and the set of reduced Young walls can be understood, interpreted as the crystal graph P of lambda. Now, I really don't want to scroll down all the slides and make you confused, but let me maybe go. Oops, I'm not doing well, right? Maybe about this much? No. Go back again. Maybe I should do that again. I'm sorry, I just didn't want to do it, but I don't know what to do. So here, what I can tell you is we can define the action of EI and FI on the space of proper Young words. But close your eyes. And let me go backward. Then this action defines the module structure for the Fock space. And we can find an LLT algorithm of computing global basis. So the remaining question is how to understand this coefficient. So we have left-hand side, the notion of proper Young word, reduced Young word, and irreducible crystal, and Fock space, and Lascaux, Leclerc, Thibon algorithm, at least for level 1. And if we know the level 1, then we can extend to level L by taking tensor product. So what is right-hand side? So what is the algebra corresponding to affine Hecke algebra, cyclotomic Hecke algebra, and finite Hecke algebra? And recently, it is settled. So the problem can be described as follows. So given a Kac-Moody algebra or affine Kac-Moody algebra, and given a dominant integral weight, we would like to construct a graded algebra H whose Grothendieck group can be identified with the negative part of the quantum group, and using induction restriction functions, if we define graph structure on the Grothendieck group, then that should be isomorphic to the crystal graph of negative part of the quantum group. Moreover, for each lambda, we must have a cyclotomic quotient whose Grothendieck group is isomorphic to the integral form of irreducible high-street module, and whose crystal structure is same as the irreducible high-street crystal. That's the problem. So it is called the categorification problem. And it was settled down by Kobanov and Lauda and Rukier last year. And the crystal part seems to be still under progress, but it's only a matter of time because we have characterization and recognition theorem for crystal graph. And what they should do is they just have only to identify what they have now. So, and Brandon and Klashoff proved the decomposition number theorem for higher levels too, using this result. And what I'm doing with my students now is to construct and generalize Kobanov, Lauda, Ruki algebras for generalized Kac-Moody algebras. And also, well, for affine cases, I'm trying to construct a good realization of B of lambda and B of infinity, like Young words, combinatorial models. Then we can define Fock space representations and LLT algorithm, especially for so-called adjoint crystals, which is level 1 for all affine algebras. We were able to do this. Then, using these results, we can prove the decomposition number theorem for all affine algebras and for all higher levels. That's enough. Thank you very much.